Hello, y'all. This is Darrell D. Berry Jr. back with some linear algebra. I'll be working on the four fundamental subspaces, which is a subject that I sort of overlooked. I noticed that it's a prominent part of a project that I'm working on that's due today, solving some problems of solving inconsistent systems. So I'll be working on that on the four fundamental spaces, trying to get a bit more understanding of that, and then going back later to the problems I was working on. So I plan on just going back and forth between sections as needed until I finish the homework or special project assignment that's due today. So a day of linear algebra. So hopefully I'll be finished by, let's say, 4 o'clock. That's my goal. So I'll be off and on until then. If you pop on, go ahead and say something in the chat. It looks like somebody just chatted just now. Maybe it didn't show yet. So if you have any questions, comments, say something in the chat. You could also respond to the video. Be sure to like, subscribe, share, join my Discord. We can chat there as well. So let's go ahead and get started. I'm still using my new setup where I have either a full book or a full iPad. So we'll start with section 3.2, the four fundamental spaces, and I'll take my time on this and we'll see if we can get a good understanding of it. So the four fundamental spaces. And in case my audio is catching a bit, I'll turn it down just a little bit, and hopefully it doesn't cause any breaking. As we have seen, two of the most important constructions we've studied in linear algebra, the span of a collection of vectors and the set of solutions of a homogeneous linear system of equations lead to subspaces. Okay, so span and span of something and AX equals 0 subspaces. Let's use these notions to define four important subspaces associated with an n by n matrix. The first two are already quite familiar to us from our work in chapter 1, and we have seen in section 1 of this chapter that they are in fact subspaces. Here we will give them their official names. So, null space. Let A be an n by n matrix. So the rows and columns don't, or at least may not have the same number of elements. Null space is the set of solutions of AX equals B and B equals 0. So the null space of A is all X in Rn. And the reason why it's in Rn is because if I have n by n, I need to have an n by something to solve for m by something. And X is the solution. Therefore, X has to be n by something, and whatever the first number is, that's the degree of the space. So whatever the n value is, that'll be the degree of the subspace. So X is in Rn, and AX equals 0, right? So null space are all the solutions of the homogeneous to write it simply. Simple enough. And then we have the column space. I may have gotten column space correctly on that part of the exam. So A is again an m by n matrix with column vectors and number of rows, that's going to be n because there's a number of columns. And these are vertical vectors. And it says AM is in R, AN is in RM. So the vectors, there's n number of vectors, but they all have m number of rows. So that's why they're in RM. But technically it'll be this way. All right. And so that's our matrix. That's our vectors that make that matrix, that span that matrix. We define the column space of A to be the subspace of Rm spanned by the column vectors. So column space of A equals span A1, AN, and RM. So the proper way to write that is CA equals span, and then the vectors uh, we have within sign for the without the slash in the middle in RM. Of course, the null space is just a set of solutions of the homogeneous linear system Ax equals 0 that we first encountered in section 4 of chapter 1. What is less obvious is that we encountered the column space in section 5 of chapter 1, as we shall now see. So let's look at this. A to So the column space of A, all the different vectors that make up A, is commas, not a plus. So if A is 1, 2, 3, 4, 5, 6, 7, 8, 9, then the column space of A equals span 1, 4, 7, 2, 5, 8, 3, 6, 9. At least that's how I'm understanding it. So let's see if that's how it is as we go along. So we have proposition 2.1, and it says Same thing is m by n. And B is an Rm, right? B is an R, that's right, because the thing on the equal sign is going to start with the first thing that the matrix starts with. So the thing on the other side, which is B, it'll have the same first degree as the first part of the matrix. And the second after the multiplication will be the uh, 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 second number of x. And now we're focusing on B. B is an Rm. Then B is the column space of A, if and only if B equals AX for some X in Rn. All right, so that seems to be the second, almost like a second definition of column space. Column space equals B is in Rm, AX equals B is consistent. Now, I do recall that when we spanned the space, it was a plus. So it looks like they do mean plus. Because if I have a matrix and I have X, then if I dot product that in, if I dot product this in, it'll end up being and that will equal B. So the span is a sum, right? So here's a proof, right? So A is m by n, B in Rm, as it should be. Then B is in the column space of A, if and only if B equals AX. So I didn't get that right. For some X that's in Rn. It's like I scrolled up a line. Hold up. But it is true, but right? So the proof says, by definition, C of A equals span A1, AN. You're going to have as many columns as uh, as many rows as the matrix has columns. And also as many columns as the X will have columns. Or at least as many columns as that's correct. Because the columns will still be for the span n by x or n by n, and this will be the number of columns, and that will end up being the last number. The n will be the last number of uh, the resultant b. So span equals a1 plus a2 an. And it says it right there. C is that span. So B is in the column space of A if and only if B is a linear combination of the vectors as we have here. We have to add our x's as well because it's literally ax equals b. All right. And the number of columns will be the number of rows. Following our crucial observation on page 53, we conclude that B is in the column space of A if and only if B equals AX for some X. The final reformation is straightforward so long as we remember that the system AX equals B is consistent provided it has at least one solution. Let's go to page 53 to see what they're talking about. Theory of linear systems. A1 dot C equals B1, A2 dot C equals A1 dot C equals B1, A2 dot C equals B2, AM dot C equals BM. That makes sense. The matrix, uh, the answer ends up being the first dimension of the matrix. That is what they mean by the star, a crucial observation for future work. What AX can be written as AX equals that. So it equals X1 and this is a vector as well. So it equals X1, A1. And it looks like he kept the same numbers. So the x's have as many rows as the matrix has columns. That's why I was able to fold over and multiply by it. And this is the same thing as x. As we do that whole column down, right? So this also equals right. So it is important to the definition. We'll go back to that part. I think we have that down. And he says, remark, if, as in section 1 of chapter 2, we think of A, the matrix A, as giving a function mu A, transforming R into Rn, then the column space of A is in Rm because B is in Rm. Column space equals column space of A equals C I'm thinking about this notation it has here, the mu. I don't know why they call it that, but we do know it's changing. So if you have ax equals b, we have m n, we have n something. That's going to equal m something. So we know we're changing x from the n space to the m space. So that's what I see that meaning. Because here it was at the n because it's starting with the second number, and now it's in the m. And we can see that in the notation R into Rm. So A, think of A as giving a function transforming into M. Then CA is a subset of Rm. Is a set of all the values of the function mu, i.e. the image of mu A. It is important to keep track of where each subspace lives as you continue through this chapter. Okay. All right. The null space NA consists of x's in plus of mu A and is a subspace of Rn. So the null space NA consists of x's, vector x's, which are inputs of A. So if this is A, x is an input of A, it equals B, assuming that it has a solution, and is a subspace of Rn. That's right, because it starts with N. No, a subspace of Rn. The null space is all the zero solutions, all the x's that solve for zero. So this would be M, N, N, M, and that is correct. All the solutions that solve for 0 will be in the n space because that's what the first letter of the thing starts with. The column space consists of these outputs of the function. Oh, I see. So null space is inputs. Inputs that solve ax equals 0, and column space outputs of ax equals b. And view A is the function. The theme we explored in chapter 1 was that lines and planes can be described either parametrically or by Cartesian equations, yes? This idea should work for general subspaces of Rn. We give a parametric description of a subspace V, then we describe V as the span of vectors V1 through Vk. Putting these vectors as the columns of the matrix A amounts to writing V is in the column space of A. So V equals the column space of A equals vector columns. Putting these vectors as the columns of a matrix amounts to writing V equals the column space of A, because those vectors are assuming they add up to B. So it's not the vectors themselves, but the fact that they add up to something. Similarly, given the Cartesian's equations for V, once we translate them into matrix form, is giving V of NA. V equals NA. Right? So V equals CA is writing them as a vector. V equals NA. It's the Cartesian equations. And that's the horizontal. Because when we solve for AX to get B, it goes across. So CA column space makes sense. Vertical column. So since the vertical is taken by V, CA, then VNA must be the horizontal. Adding them together, the horizontal sum. The vertical placement. I don't think we actually read the books there. For the appropriate matrix. So once we get the solution to the homogeneous, we have the null space. Much of sections 4 and 5 of chapter 1 was devoted to going from one description to another. Remember that thoroughly. In our present language, by finding the general solutions to ax equals 0, solutions of ax equals 0, we obtain the parametric description of Na, general solution. Parametric solution of Na. And let's obtain vectors that span the subspace. And that's, of course, when we solve for that and we get like x equals, and then we have a vector and x3 and then the vector x4. When we solve the general solution in row operation form and get this eventually. Find the constraint equations for ax equals b to be consistent provides the Cartesian equations for NA. So ax equals 0 is for the null space, so the solutions, and constraint equations the column space. Right? So we're at example 1 right now. I'll go ahead and take a break. When I come back, we'll go ahead and start with example 1 and work from there. So thanks for joining. I'll see y'all next time.